All right. Hello and welcome everyone to today's session of the Social Science Data Lab. Thanks for sticking with us through this chaotic start of today's session. My name is Dennis Cohen and I'm happy to welcome you to today's talk by Chung-hong on detecting implicit biases in large language corpora. The Social Science Data Lab, as you know, is an event series here at the Mannheim Center for European Social Research, where we provide a platform for our presenters to discuss tools and methods for the collection, analysis, management, and visualization of data in the social sciences. Our speaker today is Hong, who is a postdoctoral researcher at the Institute for Media and Communication Studies at the University of Mannheim and here at the Mannheim Center for European Social Research. He is an expert in communication science at the intersection of political communication and media, and specializes extensively in all kinds of natural language processing and computational approaches to quantitative text analysis. In his tutorial today, Hong will introduce his R package sweater that one can use to detect biases in word embeddings. Just a quick note on the logistics for today's talk. You can ask your questions at any time by raising your hand in the Zoom chat or by posting your questions in the Zoom chat, in which case I will read them out for you whenever it is convenient. That being said, apologies once again for the delay. And Hong, we're very glad that after all, this talk can take place here on Zoom today, and the floor is yours.
Yeah, thank you very much. And thanks a lot for the introduction. And actually, this is a talk that I also did yesterday at the ICA. This is a lengthy version of the talk that I did yesterday. And this is almost like an intended version of the talk. So I hope that I can give you a much fuller demo of the package sweater today, and also give you more theoretical framework of how it works. And so the first question, what is implicit bias? So here I use the term implicit stigmatization because stigmatization is talking about the negative associations with some entities. For example, here we have two sentences. Okay, I think most of you know how to read German, but the first sentence saying that the people who smoke frequently in shisha bar are criminal. And then the second one is Adam smoke often in a shisha bar. So in these two sentences, Adam is not directly said, the speaker of these two sentences didn't directly saying that Adam is a criminal. But if we consider both sentences together, we can see that there is an implicit link between Adam and also the criminality, the possible criminality of Adams, because Adam exists in the context of shisha bar or the orphaned visitor of shisha bar, and then the people who often visit the shisha bar are criminals. So there is an implicit association there, and it is not similar to the case of explicit stigmatization, because explicit one is more like a positional statement. It will say that Adam is criminal, but in here is associational. According to this paper, this is the major difference between the implicit and explicit association or implicit association stereotype. And so in order to detect this kind of associational statement that convey the implicit stigmatization, we need to know the textual sentiment associated with the context. It's not associated with the group name itself, but associated with the context, in which a group name is used. And Therefore, the recipe for detecting this kind of associations are the group names. In here, we didn't say the group names, but in the example is Adam. And then that we also call it the target. And then we also have the sentiment words. In this case, these are the attributes. So negative sentiment or the stigma. And then the third is the contextual understanding of where a word is used. In this case, we want to know in which context the word Adam is used, and also in which context the attribute, the negative sentiment, it is used. And in order to do that, the literature suggests to use word embeddings. And the word embeddings actually is to quantify the contextual understanding of words. So we can convey the meaning of a word by the context in which the word is used. This is a this phenomenon has a name, which is called a distributional semantics. The semantics, meaning the meaning of a word, are distributed in the context that the word is used. Here I give an example. For example, we have 4 different documents here. The first document saying that Berlin is the capital of Germany, Paris is the capital of France, and then Tokyo is the capital of Japan. And then the 4th document saying that cats are some favorite pet in the world, something like that. So in the first 3 documents, the words Berlin, Paris, and Tokyo, and also Germany, France, and Japan are used in a very similar context because the language construction, when they use those words, are very similar. So we could infer that the meaning of Germany, France, and Japan are similar. They have similar meaning. But the word cat is different because the word cat, we usually not use it in combination with words like capital, but something else, for example, like pet. So in this case, the word cat have different meaning to the country names, for example. And the word embeddings is actually try to quantify the differences in the contextual usage of different words. And so, as I've told you, the word embeddings is to capture the distributional semantics meaning of words based on a large corpus of textual content. So we can train those word embeddings based on a large corpus of text, and then we can study how different words are used in different contexts. And I will give you some example later. But it is a little bit different from the way that we usually represent text in text analysis. So in a regular text analysis scenario, we usually use this kind of representation of words, which we call the one-hot word vectors. So we have one row of text, but one row of a vector. But when this word is used, we just make this one or positive, and then all the other words are said negative. This kind of representation is useful in some case, but it is not useful for quantifying the semantic meaning of words, because you cannot do a comparison between 2 vectors of words. But we can use the one-hot word vector to train some word embeddings, and then the word embeddings will not be a sparse matrix, but a dense matrix. So each shell, so to speak, in a word embeddings is not just 1 or 0, but some real number. And then we can compare the vector of a word. So actually each row represent a word, but the column, well, it didn't have a concrete meaning, but we need to do a comparison of those word embeddings, word vector. So one row we call it word vector to compare the meaning of a word. So I'll give you a concrete example in the next slide. So here we have some word cluster here. So if we cluster, okay, this is from another paper of mine, but I just taken the visualization of in that paper. So you can see that Germany, Switzerland, and France, they are very close to each other. If we study the distance between the word vectors of these words, but it is quite far away from other words. For example, these words, communism, liberalism, they are much further from each other than the words that are very similar, which are also the country names. So actually, the package sweater is to evaluate the association among words in word embedding space. So we can consider this two-dimension space as a word embedding space, and then we just want to study the association between words. So and then there is a question: what is a semantic association? So actually, I've implicitly tell you what it is. So in here, we can find that the word vector for Deutschland or Germany is very close to France, but much further than Germany to cat, for example. So we can study the differences between these word vector as an indicator of an association. For example, the word vector of Biden will be much shorter to American than German. So because we use the word Biden more frequently in the context of American than German. So this is what we call the semantic association, or the associations among words in the word embedding space. But there are also another thing, which is what we call the word embedding biases. So word embedding biases are also associations, but these kind of associations are unwanted. So we don't want to have that kind of association. So, okay, the Biden American German one are what I call the legit association, because Biden is really an American. It's not a German. But in the bias situation, those associations are unwanted. So, for example, if we want to study the gender bias, so we can use two different kind of contexts. For example, the words that related to gender, she, daughter, her, and also another context, he, son, his, him, and then study the association between the contextual words related to male and female to see that kind of unwanted association. I will give a more concrete example later. But this is a warning. This is a very important warning of using this kind of methods. It is because word embedding bias is a corpus space measurement. Therefore, it is very difficult to validate. In order to validate this kind of word embedding bias, you need to have a human reader to read all the articles in the corpus and then study that kind of biases in the text. It is not very similar to the ordinary machine learning procedure. The ordinary machine learning procedure is cross-validation. So we have some coder to code the document based on a coding scheme, and then see the differences between the machine learning prediction and the human coding. It is easier because the unit of analysis for ordinary machine learning procedure is usually the document, but here is a corpus-based measurement, and it makes it very difficult to validate. And to be honest, I'm still struggling how to validate this kind of association. But in the literature, the researcher usually use these kind of word embeddings bias to predict real-life phenomena. For example, like the gender disparity in employment, for example. This provides some evidence of predictive validity, but that is not the same as the ordinary validation process, because it is just what we call the scientific instrumentalism. So if you want to know more about the text analysis, social media analytic, and also the scientific instrumentalism, I highly recommend the article by Yonghair, Yugen, and Xun at the SSCR. So there's a very fruitful debate of how this scientific instrumentalism hamper the advance of science. So very great articles. Okay, before I start this talking about this line, I should click this button first. This is the one code. So okay, with all this warning, so you need to have some word embeddings to do that kind of detection of word embedding bias. You can train your own word embeddings. I will show you how to do that in the next slide. You can also use some pre-trained word embeddings provided by other people. For example, like the Google. Anyway, so I'm sorry about that. I tried to run it again. So okay, you can use the word embeddings provided by other researchers. For example, like Google provide the word embeddings for their work to rack word embeddings, and also the Stanford group also provide the word embeddings for the graph word embeddings that they train on a large corpus of text, like the Google News or the OpenCrawl data set. And those word embeddings are usually very large. And so in this case, if it works, I don't know why it didn't work today. My package Threader actually provide a function to read the word embeddings from those pre-trained word embeddings. And if it works, so it can read a word embeddings within a very large word embeddings within a minute. But if you use Python to do that, the Gensim package also provides some functionality to read those pre-trained word embeddings. It will take 10 minutes. But yeah, actually, I don't know why it works today, but maybe I can show you how it works later. But in theory, it can be done in 1 minute because I use some very efficient C++ code here to read those word embeddings. Okay, I didn't know why it doesn't work, but yeah, let's move on. If there is question related to this, I'm very happy to demo how it works. You can also train your own word embeddings. For example, you will have a very large corpus of news articles, manifesto, for example. You can train your own word embeddings, and you can use the package Condita to do the data processing of the text, and then use the package text to WAC to train the graph word embeddings based on your corpus. I would say that the process is super easy to do now than a few years ago because now we have the R package to do that. And also the Quantita package provide a methods to pre-process the data. And so the procedure is very similar to what you do usually for doing text analysis, but there is a trick here. So you need to create a corpus of your text and then do a token. So converting the corpus to a token, the token is just, for example, I am a boy. So it converted into I am a boy. So each individual words. It is important to retain the order here. And that's why you cannot use the DFM, the document feature matrix here, because if you use the DFM here, it will discard all the information about the order of the words. And then the Quantita package provide a function called the FCM, which is the feature co-occurrence matrix. So you can convert your tokens into the FCM. So this step is RAM intensive. So if you have a very large corpus, it will take a lot of RAM. And if you use one of those laptop provided by MZES, for example, which have 32 gig of RAM, if your corpus have, I don't know, maybe 100,000 of articles, then this will break down. But I can tell you how to do that in a RAM efficient way. If you want to know that, I will tell you how to do that at the Q&A if you have these kind of questions. And then we have the feature co-occurrence matrix. So this is what we need to train the Golf word embedding. So if this step can be done, then the next step you will be usually fine, because the next few steps are very RAM efficient, and only this step require a lot of RAM, and then just type in these kind of lines. And actually the package text to VEC provide a tutorial on how to train that. So I basically just copy and paste the code from there, and then you will get your own word embeddings, WM, that you can use for your further analysis. And then now we have our word embedding. So as I have told you, there are three different things that we need to do to quantify the biases. So we need the word embeddings, we need the target, and also the attributes. And so the package Sweater used the concept of query to look for biases in the word embedding. So usually a query require at least one set of targets and also one set of attribute. But in most of the case, we need one set of targets and two sets of attributes. And I will show you how it works later. And but there's one very important thing, which is the target words should have no bias. So if you're talking about gender biases in occupations, so occupation words should have no bias. But the attribute words, they should have some meanings which is related to your bias. For example, like if you are talking about gender bias, then one set of attribute words should be related to male, and another set of attribute words should be related to female, for example. So the package provide a number of methods to quantify these kind of biases, and then the package query, the package provide a function called a query, and it required the W, which is the word embeddings, and then the S word, which is the target words, and I call it S, and then another target words if it is needed, and then 2 sets of attribute words, and then you need to specify the methods. And if you are lazy, so you can just say methods equal to guess, and then the package will select the best methods for you based on the number of target words and attribute words you provided. And then verbals will just print out more information during the calculations. And this is an example. So this is an example that we are going to reproduce the analysis of Garg et al., which is a paper in PNAS, I believe. And they try to study the gender bias of occupation words in the pre-trained Google News word embeddings. So they have some S words, which is the target words. That is, those are occupation words. And then they also have 2 sets of attributes. So the first set is words that are related to male, and then another set are related to female, and then we use the function query to query for the biases. So if I run this code, it will give you the results, and so it will give you the effect size. You need to look at the documentation of Sweater or the original paper on how to interpret this effect size. But I will just show you how, and then the function will also tell you what function you can use to further process the results. And then the first one is the calculate ES. So it just calculates the effect size. So just recite the effect size that has been displayed. And also it can also use the plot function to plot the results. And I will show you the plot function in here. So the code is the same, but we only add the plot function here. And then if we run the code, it will give you the data visualization of the bias of each individual word. For example, here we can find that okay, the word nurse and also midwife are more positive. So more positive meaning they are more associated with a female. We also have a janitor and engineer, but they are more in the negative end of the values because they are more associated with male. Okay, these kind of differences, we call them bias because they are male nurses. They are also female engineers. And we don't want to have this kind of association. And that's why we call these differences biases. And we can detect this kind of biases using word embeddings and also Sweater. And then this is another example. Okay, I create this example exclusively for the ICA. So I train my own word embeddings using the abstract from the ICA. And then we have some words that are related to data analysis. And then we have 2 sets of attributes, R and also the Python. And I want to see whether there are some PoR or PoPython biases in the ICA abstract. And we can do the same thing. And it will give you a figures that look like that. So if it is more positive, meaning it is more associated with Python, and if it's more negative or even lesser, the value is lesser, meaning it is more associated with R. So we can see that, okay, Python is, okay, computer or computer vision are more associated with Python, and then the R is more associated with general analysis, for example, like research analysis and statistics. There's a catch here because the word R is also used for Pearson correlation. So it may be the reason for this kind of results. Okay, and then this is a more complicated example, but I think this is a more illustrative example of detecting word embeddings bias. And actually the package name is derived from this paper, which is the word embedding association test by Caliskan and colleague. And so I believe the paper is in Science, I think, yeah. And in this case, the analysis is a little bit different. So it's not just one set of targets and then two sets of attributes, but instead here we have two sets of targets and two sets of attributes. And in here, we have one set of targets that is related to science or computation, and then another set of targets that is related to art or humanities. And then we have two other sets of attributes. The first set, similar to the previous one, are those male words, and then the female words. And then we can do the same thing, do the query, plug in the word embeddings, and then the S, T, A, and B. So if we run the code, it runs immediately, and then it will give you the effect size. The good thing about the effect size from the SWEAT is that it will give you an effect size that can be interpreted the same way as the Cohen D. And so in here, it is very positive, larger than 1, meaning a very large effect size. If you know how to interpret the Cohen D, it is the same way to interpret that. So here the effect size, meaning that the association of the science word with the male compared to the female are larger than the association of the art words association with male than to female. So it is a difference, and that's why it can be detected. It can be analyzed the same way as the Cohen D. And also, if you know the background of that, it is actually the same as the IAT that is usually used in social psychology to detect implicit bias. So in the paper, they compare the IAT and the WEAT, and then they found that there is a very strong correlation between the two. I can tell you more about that later, or my criticism to that later. So because this is a Cohen D, so you can convert it into a correlation coefficient, for example. So it will convert it into a correlation coefficient. So the same thing, you should know how to interpret the correlation coefficient. And then we can also do a statistical test, and then it will give you the p-values, right? So if it's p-values equal to less than the critical alpha, then you say that there is a strong gender biases in the comparison of the implicit bias between the art and the male. So I've checked with the articles as well as the author that my package can completely reproduce all the analysis in the original paper. So you can trust my package for doing these kind of things. So this is time for me to advertise my package. These are a little bit ugly to look at, but if you run the the analysis in your R console, it will give you a very nice output that look like that. And actually, I would say my package is easy to use because it will guide you what you should do next with the analysis. So it will tell you can do calculate ES to calculate the effect size, or the width resampling to do the statistical test, or if it is available, it will also tell you you can use the plot function to do the data visualization. And it is very efficient because most part of the package is written in C++, and that's why it is very efficient. And also, it is very easy to write. I mean, it is very easy to use it with the R implementation, which is distracted. And so I actually have compared the analysis using 3 different programming language. So if you use R, you just read in the word embeddings and then define the target words and then the attribute words and then do the query. So clean and simple. But if you use Python, you need to do a lot of things. So you need to read the word embeddings and then convert the word embeddings to the way that you can use for analysis. And then the same thing, define the target word, attribute words, and then do the query. So I would say the query part, I borrowed it from this package, which is called the Rifi. And then I also have the Java version here. So I hope that you don't need to write something like that in your life because it is too verbose. And but it is very efficient, I would say. And actually, this reached the end of the presentation. So the package is now available on CRAN. You can use it immediately by install package Sveta. If you like, you can also install the developmental versions. I would suggest you to install that one instead. So if you use that package, I would appreciate that you cite my articles, which is now accepted by the Journal of Open Source Software. And I also want to take this opportunity to thank the German government to sponsor the development of this package. And thanks for having me, and I'm happy to answer your questions related to Sveta or the detection of implicit bias in general. Yeah, that's all. So I will stop sharing.
Wonderful. Thank you so much for this great input, Hong.
Yeah.
We now have ample time for questions, comments, so the floor is open. Okay, Leah, please go ahead.
So first of all, I want to thank you, Hong, not just for this talk, but for another package that is probably going to make my life easier. Thanks for that. A couple of questions, actually, because I'm working with named entities mostly, which is kind of like difficult in some regards, because I usually work on, well, messy or dirty text, because all the cleaning steps kind of kill my entities. So if, for example, I have this organization which is called 350.org, which of course, if I clean it, you know, goes to just org, which makes it basically unrecognizable. So is that possible to kind of skip some of the pre-processing steps and still do this? And for example, use named entities such as this organization as my target words, at least?
Okay, so in this case, okay, I would say that you almost always need to do the pre-processing, but in your case, the pre-processing will be different because you need to use name entity recognition to first identify all the name entities in your corpus. And you can also define your own name entities in this case. If you want to do it automatically, you can use the package SpaCR, so which is the interface to the SpaCy Python package. Because why I suggest you to use SpaCR, because you can directly convert the results from SpaCR to a token object from the quantita, and then you can use the quantita to use the same process that I have told you how to train the word embeddings further, and then you will have a word embeddings that contain the word name entities. I mean, because if you process it after the SpaCR, it will contain a label after it. For example, like the word, okay, let's say Google, and then they will have the parenthesis after it, and then saying organization, for example. And then you can select those organization name based on the parenthesis after it, and then study the implicit bias using the methods that I have told you. Yeah. And I hope that I have answered your question.
Yeah, that's great. I mean, I used SpaCR and it worked, well, halfway, like it always does, because it's messy, it's text. But I have a list actually, so I can read it in and use it as a token and then convert it. So it's kind of like, well, recognized as a word in a way. So yeah, if that works the same way afterwards, that would be very helpful. Yeah, thank you.
Yeah.
All right. Do we have more comments and questions?
Yeah, actually, I have a question to Jana.
Yeah, go ahead.
Yeah, because this is okay. This is somehow related to psychology, and I want to know your feeling about this kind of associations. So yeah, do you think they work the same like we do in social psychology, or do you think it is just BS?
That's a good question. It didn't feel unintuitive what you said. So there was nothing I thought like, oh, that doesn't fit what I know about psychology. I don't know if I think I would have to think a little bit more about that, but it felt right, everything you said. So I don't think there's like an issue with that. I think that's kind of a complex question. I think like how associations are formed and how they are kind of represented in the mind and like transported into language. So I'm not sure I'm like qualified to make like a final statement on that, but yeah, I don't have anything that kind of contradicts what you said. If that works for now.
Yeah, great.
Okay, any more questions or comments? Since we're waiting for, oh, Leah, you have another question. Let's go ahead.
Yeah, I was just thinking if nobody else had an important question, you said you could talk a little bit about the RAM efficient ways to do this, because my nice little university laptop just took like a weekend to basically just compute the cosine similarities between, I don't know, like 300, 500 maybe articles, which is not that much to be honest. So if I could do that in a way that didn't, block my computer for entire weekends, that would be great.
Okay, so if you use my package, you don't need to do the looping of doing that kind of cosine similarity using native R, because doing that using native R is slow. If you do it using my package, you can do that using the function MAC. So I provide that function in the package, and it will do it more efficiently. I'm not saying that it must be very efficient, but it is more efficient than doing it using the pure R implementation. And then, yeah. And then there's another question. I don't know whether it is related, but if you want to train your word embeddings in a RAM efficient way, you should try to process the FCM, feature coherent matrix, by chunks. So if you have 1 million article, you can create a chunk of articles and then create that FCM, and then after you have all the FCM for each chunk, you can add those chunks together, add the FCM together, so that it won't break down your RAM. And this is the way that I found that that can be done in a RAM efficient way. But it is not CPU efficient because it cannot use up all the RAM to hold all the things in the RAM, but it used the hard disk to do the buffering, and that's why it can finish the analysis. I mean the training of the word embeddings.
Right. Thanks. Pavel, you had your hand up for a second. Do you still have a question?
A question just for Leah. I recently also computed pairwise cosine similarities between documents, and the performance is always horrible. So I just send you in the chat a link of a Python function which kind of implements it smoothly. Surprisingly, it's NumPy. I'm still not sure how they did the magic, but it's like the difference was with like I really created an edge list and then looped through the edge list, and I think it took me a night or something like this, and those guys did it in a few seconds. So it's I don't know how much is it, 1,000 factor. Sorry, Chung-hong, if I'm stuffing your presentation right now. But I would have a question also to Chung. Could you? I'm not from a social psychology perspective, so could you just define again the definition of bias with regard to the embeddings? Right. So when do we have a bias and when don't we?
Okay. So okay, biases are some associations that we don't want it, and then that kind of association is implicit. That a target is associated with an attribute, and I think in other papers they didn't have that kind of definitions, but I need to dig up this definition from the communication literature actually, and so if you want to know more about how the definition of that, I can quickly dump that paper into the chat. Yeah, and I think this paper gives a more communication way of thinking about those kind of biases, stereotype, and stuff like that. But if you're looking at the computer science literature, they usually didn't think about biases in this way, because if they talk about biases, they think about the biases in the downstream application of the word embeddings. For example, if we use this kind of biases, word embeddings in the later prediction task, it will give some kind of biases decision. And this is how they think about biases. But if you talk about social science way or the social psychologists, how they think about biases is, I think it will be better to read the communication or the social science articles. And also, because the WEAT is based on the IAT, and they use the same definition of implicit bias. You can also read the definition of implicit bias from these both paper, the WEAT paper and also the IAT paper. Yeah.
Thank you. I think I came into this talk with the expectation of more of the computer science perspective. That's why I was a bit surprised. But yeah, great. Thank you.
Yeah.
Okay, perfect. Do we have more questions or comments for Hong? Well, if we turn things around, Hong, do you have any questions for the audience?
I actually have okay. I've asked my burning question in my brain already. So yeah, I don't have further questions related to that.
Could you then maybe say a bit more about primary or classical use cases of the procedure that you outlined here today? So what would you say are substantive applications where researchers should pay special attention to the biases that you outlined?
Yeah, actually, we use this kind of methods to detect racial bias in news reporting. So we have trained a word embeddings based on the news coverage, general news coverage. We didn't select anything. And then we select different group names, for example, like German or Chinese or Japanese, whatever. So we have different kind of group names. And then we have two sets of attribute words. That is one set, which are the words that introduce fear. And then another attributes words, they are words that inspire admiration. And then we use the methods that I have outlined to study the implicit biases of each group names in relation to fear and admiration. And then we can plot how they play out. And then still we use the scientific instrumentalism logic to predict this kind of the biases against these different group names using the independence variable, for example, like the GDP of that original country, and also the number of Muslims in the original country. So we found that if the group names is more related to Muslim, okay, the news coverage were from Germany. So if the group names are more come from a country with a higher proportion of Muslim population, they will receive higher implicit bias towards fear rather than admiration, right? And then we also use another methods to detect the explicit bias. So we cannot see this kind of association in relation to Muslim population. And so I think this is one of the use case of that. Yeah, and then there are other articles that are doing the same thing. There's another paper from Amsterdam doing exactly the same thing, but they just try to visualize the coverage of different group names and also different occupation in the Dutch media. And I think these are the two applications that I can think of right now. Probably because I am a communication researcher, I believe that there are more applications that we can do with in political science, for example, like the manifesto or the speech that the politician made during in the parliament, for example. Yeah, we can do also that kind of analysis.
Then let me just ask a follow-up question, because I'm neither super familiar with the methodology nor necessarily with the psychological distinction between implicit and explicit associations or biases. How can we ever be really sure that what we pick up using the diagnostics that you present are in fact bias, which, if I recall, is you defined as something that or an association that shouldn't be there, or that we don't want to associate with something, from something that's intentional. So the example that you brought up, for example, was that there's implicit bias between coverage of Muslim populations and negative anxiety-related attributes in the coverage. What makes this unintentional or unwanted as opposed to just explicit and intentional?
Okay, that is a good question. Okay, and that's why we need to distinguish between the implicit one and the explicit one, because actually the implicit one will also detect the explicit one if both of them are positive. I mean, there's also both of them are associated implicitly and explicitly, and then the implicit one will also pick up the explicit one. But if we only find out there is an implicit bias but not an explicit bias, then we have more confident to say that it is really just an implicit bias. And then there's another question that is related to that, is how to validate this kind of association. And as I have told you at the beginning, it is super difficult to validate. And to be honest, I don't know how to validate. And that's why we are going to explore this kind of association using survey. I mean, I want to convert this kind of association questions into media effect questions, and to see whether we can still reproduce this kind of association in a survey if we proceed it as a media effect questions. And in the next step of the project, actually my colleague Philip Müller will do this kind of media effect questions to try to corroborate the result from the implicit and explicit bias. But I'm still not saying that this is validation, because this is just corroborative evidence. And as far as I can tell, there's no people really trying to do the validation of these kind of biases.
Okay, perfect. Thank you. Then we have another question from Sarah Wagner.
Yeah, this is super interesting. Thank you so much. I was just wondering, in your package, whether the attributes always have to be binary, or if we can expand that to multiple groups as well.
Yeah, so most of the methods require two sets of attributes. If you want to test multiple attributes, I don't think there's a method exists for that. But you can do it with the MAC to study one attribute at a time, and then compare the results from one attribute to another. Yeah.
Okay, thank you.
All right. Do we have any more questions? Last chance. Okay, then. In that case, thank you, Hong, for the great presentation and walkthrough through of the code that you presented here today. Thanks to our audience for finding your way into this alternative Zoom meeting today, and for bearing with me through the initial delay. And that concludes spring 2022 of the MZES Social Science Data Lab. We will provide you with some content over the course of the next couple of weeks. We have 1 or 2 tutorials coming up. We'll upload some recordings, including that of today's session, and we will post the event schedule for the next semester, so for fall 2022, at some point during the summer. Hope to see you again in September. Thanks for supporting us and see you soon. Bye-bye.